All right, now that we've seen how the central limit theorem can be applied, let's sketch out how this is proven. Why is this true? It's pretty remarkable how we can say something so general about any sum of random variables, and something so specific. So any sum of random variables converges or can be well approximated by a normal distribution for large values of n. So that's very interesting. So how do we prove this? So this is going to be a sketch. This isn't a formally rigorous proof. To really do this rigorously requires something called characteristic functions, which we don't cover in this course. That's a more advanced graduate level type of a topic. We're going to rely on the following fact, which we won't prove, which is that if we have a sequence of random variables such that the moment generating function of yn, which is of course the expectation of e to the tyn, converges to expectation e to the ty, which is moment generating function of t, as n goes to infinity for all t in some interval, then yn converges in distribution to y. So we're going to use that. This is called the continuity theorem. Well, let me just actually call it the continuity theorem for moment generating function. So we don't prove this theorem. So we take this as given and we let's just assume that the x's in our sequence are already normalized, so they have mean 0 and variance 1, and their moment generating function is finite for all t in an open interval of 0. Then what can we say? We can say that Sn we're defining as the sum, Zn is the normalized sum. Note that the mean of the sum is 0. The standard deviation of the sum is square root of n, and in this case, the moment generating function of Zn, e to the tzn, is by definition e to the t Sn over square root of n, m of x1 evaluated at t over square root of n raised to the power n. And this is where the proof comes in, because we're now going to actually leverage the cumulant generating function. So the cumulant generating function of Zn, remember the cumulant generating function is defined as the log of the moment generating function. And the log of this here, this moment generating function raised to the power n, is n times the log of the moment generating function evaluated at t over square root of n. So this is n times the cumulant generating function of x1 evaluated at t over the square root of n. So let's recall what the first few cumulants are, right? So the cumulant generating function evaluated 0 is 0. The first derivative of the cumulant generating function evaluated 0 is the expectation of x1, which we've assumed to be 0. And the second derivative of the cumulant generating function at 0 is actually just the variance, which we've taken to be 1. So then by what we're going to do is we're going to once again use the Taylor approximation. And what that allows us to do is to express the cumulant generating function of around U to be expanded around 0. Okay, so this is again. And then there's higher order terms. This is where epsilon U goes to 0, is assumed to go to 0 as U goes to 0. Okay. So in this case, then, for a fixed value of t, and as n goes to infinity, what can we say? The cumulant generating function of Zn evaluated at t is n times the cumulant generating function of x1 evaluated at t over the square root of n, which we've just shown we can express as n times t squared over 2n plus t squared over n times epsilon t over the square root of n, which converges to t squared over n as n goes to infinity. And therefore, because of this, by continuity, the moment generating function of Zn converges to e to the t squared, not t squared over 2. E to the t squared over 2, because the moment generating function is just e to the cumulant generating function. So going back to the continuity theorem, what we get is convergence in distribution to a random variable with moment generating function e to the t squared over 2, which we've already calculated a number of times, is the moment generating function of a standard normal random variable. This is by the continuity theorem that we cited above for moment generating functions. So that's pretty much how the central limit theorem gets proven. Except in general, we would want to use what's called a characteristic function, which is beyond the scope of this course. It's actually a surprisingly simple proof, a pretty straightforward proof, not very complicated, not very long, given how widely used, how important this theorem is in the theory of probability and statistics. The applications for the central limit theorem are, as we've talked about, very extensive. And so it is a very important topic, a very important concept to be aware of and to be comfortable with, especially if you plan to do any kind of applied or theoretical statistics moving forward at any level. We can use this theorem often to approximate a probability, as we saw in the roulette example above. And we've seen this for the binomial approximation way back, where the normal distribution can be used to estimate the binomial distribution, but in fact, by the central limit theorem, the sum of any IID sequence of random variables, provided they have a finite variance, can be approximated by the normal distribution.